Okay, so let's start the morning session. And we are very happy to have Professor Manish Jain from Indian Institute of Science, Bangalore. And Professor Jain obtained his PhD in 2002 from University of Minnesota in the US. And after that, he spent some more time in the US as a senior research engineer and a postdoc. Then since 2012, he has been a faculty member of Indian Institute of Science, Bangalore, and he has been running a quantum theory materials group. And Professor Jain has been working on computational physics and developing various methods for understanding electronic and dynamical properties of materials. And today he's going to tell us about GWPSE method. We're looking forward to his talk. So could you start?
Okay, so shall I start? Can I start?
Yes, sir.
Yeah. Okay. So good morning, everyone. First of all, I'd like to thank the chairman for this nice and kind introduction. So my name is Manish. I will be talking about quasi-particle and optical properties of materials, and which is basically I'll be talking about the GW and the method-salpeter equation. So. So yesterday, in yesterday's talks, I imagine that you have heard a lot about density functional theory, and you have learned about how density functional theory can be used to predict ground state properties of materials, right? So if you remember from yesterday's, I'll just briefly recap everything of yesterday, at least some part of it, at least in a slide or so. So the idea is that within density functional theory, you can calculate properties that are intrinsic to a system with all its electrons in equilibrium. Right, that is usually the ground state form of density functional. That's the theory that is often used, and it is sort of become like the standard model for understanding ground state properties of materials. Okay. Just as a reminder, the central quantity in density functional theory, of course, is the density. And the quantity that you derive from the density that very often that you talk about is the total energy of the system, right? So, and the total energy of the system is a functional of the charge density, of the electronic charge density, right? And you must have learned yesterday about the Kohn-Sham formulation of density functional theory, where what you do essentially is map the interacting many electron problem to non-interacting electrons moving in a self-consistent field. Right, essentially, you end up with a set of one particle equations like this, where all the interesting or the non-trivial physics goes into this object called the exchange correlation potential, and then of course there are several approximations to this, like the local density approximation and generalized gradient approximation. So this is all something that you learned yesterday. So you learned about all of this yesterday. So what can you do with density functional theory? Just as a quick reminder, you can calculate ground state properties and properties such as, let's say, if you are interested in understanding the crystal structure of a material, you can use density functional theory to calculate lattice parameters. You can use density functional theory to actually, to compute charge density, which can also be measured or inferred experimentally. Then you can actually calculate things. You can perturb the system, calculate things like phonons. And of course, you can calculate, various phases as a function of volume. You can calculate various phases and find out at which volume what phases are stable and so on and so forth. Okay. But actually, there are another set of properties that we are very interested in, and these are called excited state properties. And what I mean by excited state properties are spectroscopic properties that involve experiments creating an excited particle above the ground state. Okay, so this is not a ground state property. Now this is excited state. And essentially, what might be an experiment that where you might see something like this is the following. So imagine you have a system and you have a light source and have a detector. And you shine light on your system, and let's say you kick an electron out of the system. Right? Now, so what happens then is that you shine light on the system, you create a hole in the system, and an electron goes out, and you find out the energy of this electron. From this energy, and if you measure the momentum of the electron as well, or the sample, you can actually infer the band structure, and this is what is called the photo emission experiment that you're very familiar with. But if you do it more sophisticatedly, and then there are very sophisticated ways of doing this experiment, and perhaps Professor D.D. Sharma will actually talk about this when he talks about in his talk. Essentially, what you can do is you can actually do what is known as angle resolved photo emission spectroscopy, right? So this actually is an excited state property. So why is this an excited state property? So what do you mean by that this is an excited state property? So the idea is the following. So imagine, for the sake of argument, that you actually have this photo emission experiment. So you shine light on the system, you kick an electron out, you create a hole in the system, right? And that electron that goes out goes to infinity. So it goes to with some kinetic energy that it is going out. But as far as your system is concerned, right? You started out a system with n electrons, but you ended up with a system with n-1 electrons, right? And depending on where you kick this electron out from, in terms of total energies, right? So in terms of total energies, you actually, when you're measuring the kinetic energy of this electron, what you're inferring is the energy of the quasi-particle in the system, right? And that quasi-particle actually is the difference in total energy of two systems, not one. A system with n electrons and one with n-1 electrons. Okay. Now, in principle, you can actually calculate this as a total energy difference. In principle, this can be done. It turns out that, of course, in a periodic solid, you can never do this because you have no place to take the electron out to infinity too. Right? So you need a surface at least, or a finite system to actually talk about something going to infinity. Because if you are in a periodic solid, you take an electron out, where does it go? I mean, solid is everywhere, right? So it makes no sense. But in the case of finite system, you can actually calculate this energy as a difference of this quasi-particle energy as a difference of two energies. It turns out that this doesn't work out so well. In principle, it should work, but in practice, it doesn't work out so well. Okay. Now, there's an equivalent experiment that one can do where one doesn't shine photon onto the system and kick an electron out, but rather shines electrons into the system and looks at the resulting photons that come out. Okay, it's just the inverse of the process that we talked about. This is the direct photo emission process, shining electrons. This is something that you've all done in your bachelor's level course. You've done the photo emission measurement and so on, right? So this is the inverse process of that. This is a little bit more complicated and much more involved. But essentially, what you're doing is you're adding an electron to the system, and what you get is what you can measure then is the total energy difference of two systems, one with n electrons and the other with n+1 electrons. Okay. Now, if you think about this notion of this gap that we talk about, right? That what is it? When we you all, some of you do DFT, and we talk about there's a gap. This is the band gap of the system. What we really mean is really the quasi-particle gap of the system. What we really are trying to say is that if I kick an electron out, and if I were to add an electron, which is the electron affinity process, right? What is the energy difference between the two, right? And if I write this out, because I said these are the energy this is the ionization energy, if you wish, and this is the electron affinity. And if I take the difference, you see that this involves several systems. System with n electrons, a system with n+1 electrons, and a system with n-1 electrons, right? And here lies the problem, right? If you were to try to estimate this directly from let's say, one calculation on n electron system, you would run into problems. Okay? Now, let me point out that this process that I just described is actually different from an optical gap that you would measure in an experiment. So what would be the optical gap that you would measure? So for example, you would go to, you would sort of take a sample and you would shine UV vis light onto the sample, right? UV or visible light or ultraviolet, low energy photons onto your system. Low energy enough to actually go across the gap, but not enough to kick the electron out of it, right? So in the process, what would happen is, so you can think of that process as, okay, so I created what happens when I shine light on the system? I usually end up creating a hole in the system, but the electron that I create is not free. It's not going out to infinity. It stays inside my solid, right? And so at a given point in time, I have both a hole and the electron in my system, right? And so, of course, the first this thing would be, you might say that, look, if I have both of these in my system, then I know what the energy of this one is, and I know what the energy of this one is. So I know the energy of this optical gap, which seems quite reasonable until you start thinking about this a little bit more and start saying, well, the hole is supposedly a positively charged particle, and electron is a negatively charged particle. I have two charged particles in my system, and in principle they can talk to each other. And positive and negative charged particles, you've done the hydrogenic atom since you were undergraduate. So you find that all of a sudden this positive and negatively charged particles actually bind to each other and form what is known as an exciton, right? So in fact, when you do the measurement, when you shine light on your system and you actually find out where the system absorbs this light, it will not absorb the light at this difference of the ionization potential minus the electron affinity, but rather it would absorb light at ionization potential minus electron affinity minus the binding of between the two, because the binding is only, it's going to reduce my energy now, and that binding is going to be this exciton binding energy, which essentially is where I will start absorbing my light into the system. Okay, so the optical band gap is then nothing but the difference between the ionization energy, the electron affinity, and the exciton binding energy in the system, right? All these three quantities are involved. Okay? And I just want to point out that this quantity is in principle different from the quasi-particle energy. So the quasi-particle gap in the system, right? Because one contains this electron hole binding, whereas the other one doesn't, right? And in real experiments, people will often find that when you do the optical measurement, if the exciton binding energy is large, and this happens very often in these two-dimensional semiconductors, like molybdenum disulfide and so on and so forth, they will find that the optical spectrum will have a optical gap, which will be very different from if you actually did the ionization potential and electron affinity measurement. Right? And this is basically the difference between them. Okay. So of course the question is, we've done some electronic structure theory, and although I've tried to convince you that would not be the right thing to estimate the gap, because as I said, that if you just use Kohn-Sham DFT to actually estimate the gaps. But I said that it involves n and n plus 1 electrons and n minus 1 electron systems and so on and so forth. But is there some simpler way to understand why Kohn-Sham DFT would not give us the correct quasi-particle or optical gaps of the system? You have a question? Okay. Please feel free to stop me if you have a question, by the way. So Kohn-Sham DFT, as you've seen, works incredibly well for understanding the ground state properties of the system. But if you remember, if you think about the Kohn-Sham eigenvalues, right? They were really Lagrange multipliers that we had introduced to put in the constraint that our wave functions, the one wave functions are orthonormal, right? That's how you got those Lagrange multipliers in, right? And it turned out when we solved the Kohn-Sham equation, those Lagrange multipliers looked a lot like like a one electron, showing their equation, and we started interpreting them as bands, and we started interpreting, at some level, Kohn-Sham DFT never said that this has anything to do with the electron addition and electron subtraction energies in the system. It just looked it looked very enticing, and so we may start interpreting it in that way, but that was not really the meaning of the Kohn-Sham eigenvalues, right? In fact, these eigenvalues, the Kohn-Sham system, if you remember, was a non-interacting system that you had constructed to give the same density. All that was guaranteed is that the density is exactly the same. Right? The eigenvalues had no physical meaning. Right? So, in fact, if you start interpreting them as electron addition and electron removal energies, that wasn't supposed to happen, right? So that is something that one needs to keep in mind. Now, of course, you also learned yesterday about generalized Kohn-Sham methods, where you add a fraction of exchange to actually, to do the mapping, right? And there you can actually start thinking a little bit more formally and start asking whether this still has the meaning of electron addition and electron subtraction energies. But again, it's a map, right? It is supposed to, for all values of this coupling constant. I don't know whether you guys did the full derivation of the. Did you guys do the full derivation of the generalized Kohn-Sham? No, okay. So there the interpretation might, you can start to see, and you may be able to fit at least one more eigenvalue to the gap. But again, things are a bit iffy over there, because in principle, whatever value of exchange you pick, in principle, all of those systems are supposed to give you the same density. In principle, of course, in reality, that doesn't happen. And again, the meaning of the eigenvalues there is a bit iffy. And while you can recover some of the shortcomings in the Kohn-Sham gap by using the generalized Kohn-Sham, it is not guaranteed. Okay? There are other ways of fixing the there are other ways of fixing this DFT. And in fact, Prasenjit and Manoj Harbola, who were speakers yesterday, they actually have worked on functionals which describe excited states properly. Right? Functionals which will actually work to give you the gaps current. Right? So but you have to, your usual Kohn-Sham stuff will not work. Right? You have to do something more and think a little bit more carefully about the problem to figure out what is the correct way of getting the gaps out of these. Okay, so in general, what one can say is Kohn-Sham energies cannot be interpreted as removal or addition energies, except actually there is one exception to the rule, and maybe you discussed this yesterday. Except the highest occupied molecular orbital in a finite system is supposed to be correct. It's supposed to represent the ionization potential. Okay? And this has to do with the fact that, if you think about the highest occupied level in a finite system, the way the density decays, basically the highest occupied one determines where the density is decaying, farthest out. How it decays, it basically is determined by that orbital. And its energy has to be correct because the decay is actually related to how the density decays is related to that, and because the density is correct, then therefore this has to be with the correct ionization potential. Okay, but most things that you will use, for example, if you use LDA and GGA, they will not give you the right value. Okay. So with all of this, just as a thing. So let's say, for the sake of argument, you decide, what, this is way too complicated. I'm just going to do DFT and let's see what do we get. Right? So here I've plotted the theoretical band gap versus the experimental band gap. And by theoretical band gap, what I really mean is just the Kohn-Sham energy difference, right? Which I just said you should not use as the band gap of the system. But let's say I just said, okay, I will just do it anyway. What you find is that for a large variety of materials, and this is something that you have probably learned yesterday or know from before, you will find that the theoretical band gap underestimates the experimental band gap, right, by a lot. And this is standard. On the right, what I've done is, imagine, for the sake of argument, this is for silicon, that this is the dots are the experimentally measured absorption spectrum for silicon, or the imaginary part of the dielectric function. So imagine, for the sake of argument, you said, you know what, let me fix the gap. I know the gap has to be fixed, let's fix the gap. But let's not let the electron and hole talk to each other. Maybe the exciton binding energy is small, and maybe it doesn't matter anything, right? It turns out that if you actually don't take the electron-hole interaction properly into account, the blue line is what you get if you don't take the electron-hole interaction into account. Okay? Now, what I hope to convince you and what I'm going to tell you about are the two theories which are related to the red dots that I'm talking about. So here, the first one is basically the GW method. And here what I've plotted is for the same set of materials. What has been plotted here is all the band gaps that you get, the theoretical versus experimental band gaps. And you can see that while there is some scatter, this is doing a lot better than what your Kohn-Sham eigenvalue difference was doing. Okay. And over here, what I've done is, what has been plotted is the absorption spectrum calculated with the Bethe-Salpeter equation. And what you can see now is that, not just qualitatively, but also quantitatively, it actually matches very well with experiment. So I hope I have convinced you that it is worthwhile to listen and pay attention to and learn about the WBSE method. Yeah, go ahead. Sorry?
It's LDA, right?
It doesn't matter. You can do PBE, you will not be able to distinguish it. Meta GTA and all will also probably not. See, there's as you know very well, there is this derivative discontinuity, which is not captured in this process, right? I mean, you can actually say, if I were to ask the Kohn-Sham, if I were to go back and say, okay, you know what, I want to fix Kohn-Sham. Kohn-Sham is what I want to do, but I want to fix what is the error that I make and why is it that I make the error. So it turns out that if you add an extra electron, the potential changes discontinuously. Right? That is what is known as the derivative discontinuity. So if you plot, for example, energy versus number of particles, the energy versus the number of particles is a piecewise linear function, which means that when I join two lines, it's not a linear function; it's a piecewise linear. So between let's say 5 electrons and 6 electrons, it is linear, and 6 and 7, it is linear. But at 6, the slope from the left and the slope from the right is not the same. And that slope, the difference in the slopes, so basically this is related to the ionization potential. And what it turns out is that most functionals will actually draw a very smooth parabola, and that's the reason why they miss out on this exact derivative discontinuity. They have some part of the discontinuity, they have some part of the derivative, which is whatever would come from the parabola, but they miss out on some of the part. So, and I think most functionals do that, unless you do Hartree-Fock actually does the other way around. You just said, let's do Hartree-Fock. It actually, it is not piecewise linear because it doesn't form a parabola, but between 2 points, it actually forms a inverted parabola. And so if you, in a very, very naive way, if you said, well, if I mix the two up, maybe I can make the whole thing linear. And, in a very, very naive way, although, there's a very good formal basis for all of this, generalized Kohn-Sham does some people. Does that sort of answer?
Yeah, I just can't tell me it could be proved related.
Yeah. Correct. But I don't think PBE gaps are very different from LDA gaps. I mean, maybe it won't be this bad. Maybe it will be somewhere over here. But,
Not PBE, sir. Definitely PBE.
Okay, you're thinking of meta GA or
what is the? I have seen some cells. They are now developing function which takes care of this within this.
Correct.
So maybe up to the meta-GA level, it could be a little bit better.
Yeah, no, I agree with you. So that's what I said, right? There are now, but there are things that have to be designed specifically for keeping this thing in mind, right? And if you design them, then perhaps there are general methods for this, and hopefully that comes about. Yeah, certainly. Yeah.
Isn't there also, apart from the derivative discontinuity, there's also the self-interaction correction?
Yeah, absolutely.
Which is also a component to the.
Absolutely. That's right.
So that would not be.
That would not be captured unless you do the SIC kind of functions, right? Self-interacting corrected like functions. Right? Yeah. No, absolutely. So, what Priya is pointing out is that when you take the density and when you do this, there is in the way that we do DFT, there is actually self-interaction that the electron actually sees the potential which was caused by the same electron. And there are ways to correct that. Now I think there are gauge invariant ways to correct that. I would like to say, but I'm not. It used to be that they were not gauge invariant, but I think there are now ways to correct that. But the idea is that there are people are actually trying within DFT to actually fix this issue as well. But there exists this whole framework of many body perturbation theory, which I'm going to tell you about, which already takes this difference properly into account. And it's expensive, but I hope I've convinced you that at least it's worthwhile to look at. Yeah. So that would be just the electron affinity and analytic potential experiment. So of course, in a real system, you need a surface, right? Because as I said, if I take an electron out, I need to be able to take it out to infinity, right? If they do it on a surface, then they would actually from the surface they would actually measure the electron affinity and the analytic potential, take the difference. That would be the quasi-particle gap. Optical spectrum is just you shine light and look at what like your Beard-Lambert's law, and you look at the wavelength dependence of that. This is optical. These ones are not optical bands. These are quasi-particle gaps. These are quasi-particle gaps. These ones are optical. This is an optical experiment. Yeah? Yeah. Okay. So what is this GW approximation? So what is this about the GW approximation, and what is so this is this paper. This was actually proposed by Lars Verdien. And essentially, this is the paper which he proposed this in 1965. And if you think about it, Kohn-Sham equations were proposed in 1964. This is 65, so this is right about the same time. So what this paper says, and this is the abstract from the paper that I have just reproduced here, a set of successively more accurate self-consistent equations for the one electron Green's function have been derived. They correspond to an expression in a screen potential rather than the bare Coulomb potential. So we'll talk a little bit about what this is. But because it's a tutorial, and I'd like to point out something which I don't think you will see anywhere in a modern paper. This is what it says at the end of this abstract. Okay, you can go and look at there. I wouldn't dare to put this in an abstract that I write in this day and age. There is not much new in principle in this paper. Right? The emphasis is on the development of a numerically manageable approximation scheme. Right? So there's something to think about. Just to give an idea of how popular this has become. This nowhere looks like the graph of any of the Kohn-Sham papers. But just to give you an idea of that, this is also becoming popular. I thought I will, this is I've taken from Michele Agostino's slide. Essentially, till mid-60s, of course, this was created in mid-60s. But for a very long time, there was not much activity in the area. It has gradually been picking up. And part of the reason why there wasn't much activity in the area is because this is computationally very expensive. And so we'll come back to what is it that one needs to calculate and why is this expensive and so on. Okay. So the idea is that we are interested, and as he said in this abstract, that he was interested in the one electron Green's function. Right? So what is the one electron Green's function? The one electron Green's function is just given by this. This is the expression for the one electron Green's function, where the psi n naught is the exact n electron ground state. So basically, it satisfies the Schrodinger equation. And what has been done here? This is written in the interaction picture, and so these are nothing but your this is the field operators these are the field operators in the Heisenberg picture, and so this is what the expression becomes. T is just the time ordering operator. Okay, so what does this do? Essentially, if you take this expression and if you said, okay, the time ordering operator, if T is greater than T prime, then you write the things in this way. If T is less than T prime, then you switch the order. Right? Then you're supposed to switch the order of the two operators. And because they anti-commute, you have to change the sign. Okay. So now, if you think about this expression for a little while, you can look at this and you can say, okay, look, what does this actually show you? this shows that you're sort of creating a particle at a position r and t, r prime and t prime, at a time t prime, and at position r prime, right? And you are annihilating a particle at r and t. It's the amplitude of that process. Okay? And if you look at the other one, you first destroy the particle, right? Because the time ordering is in this way, right? So you first destroy the particle at r and t, and then you put back another particle at r prime and t prime. The amplitude of that process, right? So this is basically nothing but your Green's function. This is just the definition of the Green's function. You can, because you can write it in this way with braces and say when t greater than this and t less than this, or you can put the theta functions, the Heaviside function, to actually just write it in one expression and write it, right? Okay, so what I would like to show you is why is it that he was interested in the one electron Green's function, and in particular he was interested in the poles of this one electron Green's function. So let's see what do the poles of this Green's function give. So what you can do is you can take this expression, right, and you can insert a completeness relation at this point in both these expressions. And what happens is when you insert the completeness, is you can simplify, because these are just the field operators and you've inserted complete, eigenstates, right? You can operate, for example, when you insert completeness, you can operate this, the Hamiltonian part of this onto the left or onto the right, and you will get the corresponding energies out. And essentially what you will see is, this is just simple algebra, very simple algebra. If you do this, you actually get something that looks like this. Now this looks very complicated, but if you Fourier transform this, you get the quantity which you are very interested in, which is if you just Fourier transform it in time, you notice immediately that the poles of this Green's function are actually this energy differences. And if you remember, this is the kind of quantity that we were interested in when we were interested in the quasi-particle energy. The energy difference of a system with n-1 electrons and n electrons, and n electrons and n plus 1 electrons. Right? Those are the energy differences that we were interested in. And the poles of this Green's function are exactly the quantity that we want. Okay. All right. So the argument is that the Green's function contains spectral information on single particle excitations. That is, the Green's function contains information when you change the particle number by one. Add a particle or remove the particle. The one electron Green's function contains that information, right? So what we would like to do then is to figure out a way to calculate the poles of this Green's function. Okay. Yeah.
Here, all the energies are still in any body.
Everything is still in any body basis. Yeah. Yes, that's right. Because when I actually wrote the energy differences, so the energies are, this is indeed, all the energies are in many body basis because we actually inserted a complete set of many body states. That was the sequence. Yeah. Okay, so the poles of the Green's function give the corresponding excitation energy. So that's the quantity that we would like to calculate. Yeah. So if I look at the imaginary part of the Green's function, and if I just say that let's calculate the imaginary part of the Green's function, 1 by pi to take care of the contours, and because when you do the contour integration you have 2 pi and things of that kind. And so, but anyway, you multiply by 1 by pi and take the imaginary part of the Green's function. This is called the spectral function. Okay? The spectral function, you can see, is a function which has some amplitude, something in the front. But in energy, it actually is peaked at the energy differences that you actually were interested in, which are the quasi-particle energy. Right? Now, in the ARPES experiments, or in several ARPES experiments, they actually Fourier transform the real space coordinates as well, and they go to k, to momentum. And this is exactly the quantity that they measured, the spectral function that they measured.
The Prabhakar from the online participants
Yeah.
raised a hand.
Yes, absolutely.
So you can unmute and say. Hello?
Hello.
What's the question in chat box?
Yes, yes.
Okay, I will write on the chat box. Thanks.
Did you check?
He will write in the chat box.
Okay, so shall I go on or should I wait? Yeah.
You can ask me, already we have-
Yeah.
Factor eta for the analytic community.
Yeah, so you put in this eta. So because what happens is, as when you do polls and when you do complex contour integrations, you always know that you have to add sometimes an eta to make sure that you regularize the integral, right? Otherwise, things start to blow up. So you have to add a small eta. You can take in the limit. You actually take eta going to 0.
But that basically gives the quasi-particle body lifetime, right?
Well, no, this eta is just a parameter that I've added by hand. Okay, to actually give you, so this has, the broadening in the Green's function is related to the lifetime, but it should not be related to the parameter that you added. Right? So there is a real process by which the quasi-particles broaden, and we will talk a little bit about that, right? But this eta is not related to that. What you're supposed to do, because this is just a parameter that you add to regularize your integral, right? To make sure that your integral doesn't go to infinity. Okay. So in principle, you're supposed to take the theta going to 0. Yeah. Yeah.
Right now, the main function and the actual wave.
Yeah. Right now, it is all formal. No. As far as I know, there's nothing approximate over here. This is exact, right? Which means that it is also pretty useless, right? Because it's formally exact, and unless you can do a formally exact calculation, you cannot, But what it shows you is that the poles is which is what I wanted to show. Is that the poles of the Green's function give you the quasi-particle energy sector. That's the demo case. Yeah. So has he written the question? I can. Okay. Okay. So just to give you again to re-emphasize this physical interpretation of the Green's function. So what is this Green's function? I said it a few minutes ago, but let me say it again. So for t greater than t prime, essentially what you're doing is you're creating a particle at r prime at t prime, right? So and then you let the system evolve, right? And then you destroy a particle or an electron in this case at r and t, right? The amplitude of this process is basically the Green's function. And for the whole, it is exactly the other way around. You first destroy a particle at r and t, let the system evolve, and then you actually put a particle back at r prime and t prime, and the amplitude of this process is basically what your Green's function is. Okay. So now this is all very good and well. So we have we know that we are interested in the Green's function, the one electron Green's function, and it poles will give us the quantity that we are interested in. Yeah.
Take care of the excite of binding energy.
This doesn't. This doesn't. Because if you see at a given point in the system, we added one particle. The exciton comes from the talking of one particle to its to the electron and the hole talking to each other. We never added two particles at the same time. So we will come to that a bit later. Yeah. Wait, when do I have? I have half an hour, right? Yeah. Okay. So now the thing is that okay. So we are convinced that I hope I've convinced you that the quantity that we need is the poles of the one electron Green's function. But the question that comes to mind is okay, fine. I'm interested in this quantity. How do I calculate it? Right? How do I get this quantity? And so for that, what we use is what is known as many body perturbation theory, and this is a theory for calculating the Green's function. So just like in DFT, you had the Kohn-Sham equations, and you derive everything for the Kohn-Sham equations, and you put down the energy functions and everything. You can actually show, and this can be shown formally. I'm not going to do that here, but this can be shown formally that the Green's function can actually be written. The interacting Green's function can be written in terms of the non-interacting Green's function and a quantity called the self-energy. We will discuss this in much more detail in the subsequent. Okay. Another way to take your DFT equations, you can actually write the DFT equations in a Dyson-like form. This is called the Dyson equation, by the way. Okay, you can actually write the DFT equations in a Dyson-like form, just to show that that can also be cast in the same language. You can actually write the Green's function for the DFT in terms of the non-interacting Green's function, and here the self-energy is actually replaced by the exchange correlation potential. Right? Just like the exchange correlation potential had all the non-trivial and all the interesting effects. Right? Similarly, the self-energy quantity that we're going to talk about has all of those things put in. Yeah. You can equivalently, just like you can write a Kohn-Sham equation, right? You can actually write a quasi-particle equation. And what happens here is that you have exactly a very similar looking equation, right? If you look at these two equations, they look very similar, except the E's are replaced by EQP. Okay, fine, that's easy. That's just the eigenvalue. But you also notice that this quantity is replaced by, this quantity is replaced by this. You had a BXC of R, but now instead you have a much more complicated object, which is called the self-energy. So all the interactions, all of this business that we're talking about is actually included in this quantity called the self-energy, which will help us in calculating the Green's function and its poles. So yeah.
So this Dyson equation.
Yeah.
Here the Green function is now in the single particle phase.
It's in the single particle. Yes. So the quasi-particle approximation has been made to get to this. Absolutely. So from a many body basis to single. Yeah. So I've done that. Yeah. I've done it. But the important thing to notice is that this self-energy is now a non-local object, but not, you've seen non-local objects for VHC, right? You learned about generalized Kohn-Sham thing, right? Where the exchange operator was there, right? That was also a non-local object. But here it is a little bit beyond just being a non-local object. It is also energy dependent. Right? So we need a way to actually find out what the self-energy is. So the big question then becomes, okay, to get the Green's function poles, I can have the non-interacting Green's function and I need the self-energy. So now you've actually taken the problem and you set something into some other problem, which is the self-energy, but you have actually not solved the problem. Right? Just moving variables around and just transferring the problem around. So eventually you have to do something, right? You have to make an approximation somewhere, and that's where the GW approximation will come. Okay. So this was actually a paper written by Lars Hedin, probably the last review paper perhaps that he wrote before he passed. And essentially he describes what the GW approximation for the self-energy is in a very, very nice way in this paper. And what he says is, I've just taken the part of the abstract and highlighted it for you. The GW approximation extends the well-known Hartree-Fock. So you all know about Hartree-Fock approximation. Right? You all know about Hartree-Fock? Yes. So it just takes Hartree-Fock and it extends it essentially by replacing the bare Coulomb interaction. In Hartree-Fock, you have psi star divided by r minus r prime. Right? So what he's saying is, instead of taking 1 over r minus r prime, I'm just going to take that as the v of r minus r prime. That is the Coulomb interaction. He's going to replace that with a different object, which is called the dynamically screened potential W. Okay? So the V, the bare interaction, the bare Coulomb interaction, is replaced by a dynamically screened interaction, which is called a potential called W. And essentially, what happens is in Hartree-Fock, you can actually write it formally as the self-energy as IGV, where V is the bare Coulomb interaction. You can show that it's exactly the same. It's exactly the same Hartree-Fock that you know and understand. It's just that it is written in a Dyson-like form, and the self-energy is IGV. And what he said is that instead of using IGV, we will use IGW, where now this W is a dynamically screened potential, and just like the Hartree-Fock set equations, this is actually going to be a self-consistent set of equations that we saw. So just so that we know what we're talking about, if you take the self-energy for Hartree-Fock, yeah.
What is the physical meaning of theta? It's the definition of single particle Green's function. How will you choose this for the numerical calculation?
Yeah. So the physical meaning of eta, the eta has no physical meaning. It is just a simple regularization parameter. Okay, you have put in so that your integrals converge. You have to make that eta go to 0 at the end of everything that you do. So if your results really depend on eta, then you have a problem because they should not depend on eta. It's just a parameter that you put in, and you have to take the limit of this going to 0. Now, of course, that's easier said than done, but that is what formally that's what it means. Okay, it is very you almost want to interpret that as a lifetime, but this eta is not the lifetime. This is just a regularization parameter that we have. Okay, yeah.
It's a party for.
Yeah. Yes.
So what people have done, they try to make it a local code.
Yes. Yes.
So have the same thing has been done in case of basic question.
The GW equation? Yeah, it hasn't been done yet. Right. So this is actually an interesting question that Amit is asking. So some of you who already do DFT might be familiar with something called local heart rate walk. Or if you read Madeline's book, at the end he talks about this is basically the idea is that look, this is too complicated. It is non-local. I don't want to deal with it. Can I make a local approximation? Right. And he comes up with a way of approximating it with a local potential. And the question that he's asking is, can something similar be done for GW? In principle, nothing stops you from doing it. Of course, nothing stops you from doing anything. The question is, how manageable is that approximation, and how complicated is that local approximation, and whether you can actually it is a numerically tractable scheme or not. That I don't know. But as far as I know, it hasn't been done. Yeah.
What is the definition of G?
GDFT is just the Green's function, the DFT Green's function, right? Like for example, in your ENM, you learn about the Green's function, right? You write it as an outer product of two wave functions divided by E minus E. If you have one electron system, then that's just the definition. Or if you wish, H minus E times G is identity. That is the definition of the Green's function. So if I have the DFT Hamiltonian, so I can just say H DFT minus E DFT times G DFT is identity. That's the definition. Right? Just like if I have the one electron states, I can just construct it by expanding this in terms of one electron states and writing it as an outer product, dividing by the energy differences. Right? You're familiar with that, right? So it's just the outer product of I don't know. I guess I didn't have a. Maybe I can write it. So G DFT of R and R prime will be sum over all one electron states, let's say I, and let's say psi I of R here. Yeah. So this is also a function of T. Yeah. Okay. Okay. So the idea then is okay. So the idea then is so your regular Hartley form, and the regular Hartley form can be written as I times GV. That is the self energy. If I were to write it in a Dyson-like form, it is IGV. This, if you write out in terms of what I've written out over here and try to expand it, this just becomes this expression. Okay, because there's an energy table that you have to take, that you have to already do, and this is what it becomes. Now, in the GW approximation, what has been done is that the bare Coulomb interaction V of R minus R prime is replaced by W R R prime of T. Okay? And so now the first question is, what is this W, right? And this W is nothing but the screen Coulomb interaction. Okay, essentially what that means is that, see, if you're in a solid, right? If I put two test charges, right? How do you think the two test charges talk to each other? Do you think the two test charges will talk to each other with 1 over r minus r prime? In principle, yes. But there's all this other stuff around as well, right? Yes? So, if I give you a dielectric medium and I put two test charges, what do? You basically replace 1 over r minus r prime with 1 over epsilon r minus r prime, right? And essentially that is the idea. That what we're going to do is we're going to now write this in terms of epsilon inverse v. And in the solid, this is very important to write it in terms of epsilon inverse v, because you can show that this is a better way to write, because in principle, you can write the series and everything converges, everything should, the whole system works, whether it doesn't know about all the quantities that we define in our head. Everything works out, right? But if we define our variables in a proper way, we can actually get things to converge, and the sums are convergent in series very well, right? I mean, that's something that you are all familiar with. And when you write out certain series expansions, if you club terms in a certain way, things converge much faster than if you just try to do the brute force sum. And sometimes the brute force sum may not even converge, right? Or may not look like it. So it is something somewhat similar idea. And you actually write the same terms, but you write them in terms of epsilon inverse v. And that is actually just a resummation of the dichromatic expansion. And that is basically what Lars Levein's idea was. And what he said is that you can actually take only the first term, right? Only the first term in the expansion, just like in Hartree-Fock, you have only one term. Here, of course, you can only just take the first term in the expansion. And it turns out that in most weakly correlated systems, this actually is good enough. So whatever results I showed you for the materials before, it works out pretty well if I just take the first term in the expansion. So this is in the series of firsts, right? I'll talk about several first order and first listing and first listing. This is the first, if you wish. So this is the first term in the expansion that we're taking in the GW expansion, and this, it turns out, is a pretty good approximation for weakly correlated. Yeah. Sorry? No, it's the same Green's function. So, I mean, it has to be solved self-consistently in both cases, because in the Hartree-Fock set of equations and in the Dyson equation, you have to also solve.
In the series expansion of G for the GW, you mentioned that there will be self-energy term. But
Correct. So this is what the self-energy is. So on the left-hand side, you have G inverse is G naught minus sigma. And sigma has G in it as well. So this is sort of a self-consistent set of equations that you have to solve. Just like in Hartree-Fock, these wave functions have to be determined self-consistent, right? Yes? So it's the same idea. So if I go back, for example, if I go back here, this will be written in terms of the wave functions and the W, right? So it has to be all solved self-consistent. Yeah.
So we have a question from Shivalika Sharma.
Yeah.
Can you explain what do you mean by poles of green functions?
Well, the poles of the Green's function are, just like in a complex analysis, when you talk about poles of anything, the poles of any object are where the function, where the denominator, for example, goes to 0, right? And the function diverges. That's essentially what in the complex plane. That's essentially what you mean by the plane. Yeah.
but it's corresponding to some set state. I mean, it's like
Corresponding to?
some excited state.
Yeah, the poles of the Green's function, physically they mean the excited state. But I think the question was about what are poles?
Oh.
I think that's what I understood it as. Yeah.
One more question.
Sure.
From Khushbu.
Yeah.
As you said that only Kohn-Sham energy of the highest occupied molecular orbital is equivalent to the ionization energy.
Yes.
So why Kohn-Sham energy of the lowest unoccupied orbital can't be equivalent to the electron affinity?
So that's a very good question. The reason for that is the only physical quantity in Kohn-Sham analysis is the density. And the unoccupied orbitals don't contribute to the density. So there is no way for you to actually infer anything about the unoccupied, the electron affinity if you were to associate it with the unoccupied orbital, because you actually don't occupy it. So there's no meaning of so there's no density that comes from unoccupied orbital. So therefore, you cannot actually relate it. Yeah. So okay. So it's okay. This is the slide for both the talks, so don't worry. So this is not just for one talk. So if you think about the photo emission process, right? So let's think about what is the photo emission process and what is it that we are actually doing when we shine electrons in a system. So here I have sort of given this very cartoonish picture, which is adapted from some slides by Madhav Gandhi. Basically, what you do is you have, let's say, a set of electrons and you kick an electron out of the system, right? Now, when you are thinking of Hartree Fock, when you think of Hartree Fock and you kick an electron out of some model, what you're really saying is that in some sense, the rest of the system is not responding to actually screen this extra charge that you created, right? Whereas if you look at the GW picture, essentially what is being said is, when I kick an electron out of the system, right, the rest of the system is responding to screen this charge, and the effective potential from this charge is not 1 over r, but rather 1 over epsilon r, because the rest of the system responded and actually screened this charge out. And because it screened this charge out, this additional charge can now interact with the rest of the system, and this is basically, there's a polarization that comes in and there's a screening that comes in. So I need to figure out how am I going to describe this polarization. When I create, what is this? How does my system respond? If I create a charge, what happens, right? And so this we will do within this this thing called the random phase approximation. Basically, just a very simple way of finding out how a system works. You probably learned about this in your linear response kind of stuff. But essentially, then what we're going to do is this extra charge and its polarization charge, we will basically make them interact classically, just like we do in Hartree Fock, and that. With this additional charge and the induced charge, that basically, if we take the classical interaction between them, describes the physics problem. Okay. So what is the difference between Hartree Fock and this? The fact that my system responded to my charge, the extra charge that I put in, right, and it screened that charge, and that leads to this induced charges and so on, and that is very important in a solid. And if I don't take that into account, I will not describe the physics problem. Okay. Yeah.
What is the role of RPA here?
So RPA, so when I need to discuss, as I said, what will happen? I add a charge, the system responds, right? So I need to know how the system is going to respond when I put a charge, right? So there's something called polarization, right? So when I add a charge, then the system will polarize. So that I will describe within RPA.
The random phase.
The random phase approximation. Yeah. So the way to think of these quasi-particles then is if you imagine that you have a field and there's a horse running in the field, right? And in India in a field there's usually dust, right? So if there's a dusty field and there's a horse running in the field, the quantity that is running in the field, the object that is running in the field is not the horse, it's the bare part, right? Instead, it is the horse along with the dust cloud that is kicked out, right? Because that is what you actually see when you are far away from the phone, right? And that's actually what the picture from matter. And essentially what they're saying is that the particle actually gets dressed, okay? Or with this cloud around, right? And and this cloud is what is known as is basically the polarization cloud around the particle, which screens the interaction of this particle with the rest of the system. Okay. All right. So what will happen if you actually do the measurement of this vector function? What you find is that you will, when you do the measurement, if you just had the bare particle moving, then essentially this particle will be completely non-interacting. Within Hartree Fock, for example, you have an eigenvalue and you have a delta function corresponding to the energy eigenvalue, and that is where your spectral function is peaked. Okay. But when you do GW, or when you actually do a real experiment, forget GW for a second, if you do a real experiment, then what you get is that this particle actually, what you see is not just a single spectral function peak. Okay? You actually get a broadened peak, and that is what is related to the lifetime of the particle. So this is basically, this comes about not from this can be associated with an effective broadening of the Green's function. But really, it actually contains a large number of ideal states inside this peak, right? Where the particle can actually be capable. And sometimes you will also get things like satellites and so on. Okay. So what we would like to do is to figure out where this peak is at with the GW approximation and figure out how to calculate its width. Yeah, which will tell us the lifetime. Yeah. Satellite is that, in principle, this has to integrate to 1, right? This peak doesn't contain all the spectral weight. So what the main quasi-particle peak doesn't contain, if you're integrated from, let's say, from here to here, right? It's 0.8 or 0.9, right? I had one particle. So, I removed one particle. I have to have a spectral function of one particle. I have to integrate to 1. Where did the rest of the weight go? If you look carefully, it turns out it goes to other things. So, for example, a particle, when it is going out, it can scatter many plasmons and lose energy. And therefore, it will actually go to, you will actually get some peaks over here and so on. So, there are other processes that will also be present in a real system and will lead to satellites. But, what we are interested in mostly is in the quasi-particle, the main peak, the big peak. Yeah? Does that sort of answer your question? Interacting means a real system. There's a system where you put a particle, all the particles are talking to each other. So if I take let's say Hartley Fock, right?
So that's not electron only connect.
No, this is not electron control. Yeah, sorry, I use that interchangeably. Yeah. But what I mean is a system interacting with its, a particle interacting with all the particles inside the system. That's what I, yeah. Okay, so when you work this all out, this is where everybody's at. Oh, wait a minute. So far, everything was very nice and simple, and suddenly, there are these 5 equations, and they all have, 3 coordinates and 4 coordinates and so on. I will just say the following. At the end of the slides, okay, which I will not talk about, hopefully, there is a derivation of how you get these set of equations. There is a very nice way of deriving these equations from the single particle Green's function and how you will get these equations from there. So what I've done is I've taken this Schwinger way of deriving things where you add an external field and you make that field go to 0. And you take derivatives with respect to that, and with that you can actually derive a free set of self-consistent equations that you're supposed to solve. And this quantity is nothing but your self-energy. Okay, that we're supposed to solve. Okay, these are scary and very large, big set of equations, but that's not what we actually do. This is formally, this is what has to be done. This is what Hedin derived, right? But then he said, and this is the remarkable part. Then he said, essentially what you could do is take only the first term in this. Forget everything else. Remove all of these other things and it will simplify it in a second. So essentially what he said is, you have to iterate this entire process. You start with sigma equal to 0. So your G is G naught, because if you remember, G inverse was G naught inverse minus sigma. If I set sigma to 0, then this G is G. Sorry, G is G naught. Then what that implies is that this function, this gamma function, vertex function as it is called, becomes 2 delta functions. This becomes a very simple looking object, product of 2 Green's functions. You are supposed to solve this self-consistently. There is a way of solving this self-consistently, and we'll talk a little bit about that. And then sigma is written as just IGW, and that's it. That's it. You can stop there, right? For most weakly correlated systems, this is good enough. Yeah. Yes.
D is the bare Coulomb and
P is the bare Coulomb and W is the straight Coulomb. Is the polarizability, useful polarizability. So you can show that if you start with this and you iterate this, if you say, you know what, I want the exact answer. I'm not going to stop at the first one, right? I want the exact answer. You can show that if you keep iterating this, you will get the same diagrammatic expansion as you would get from Wick's theorem. If you know, I don't know if you're familiar with Wick's theorem, then yeah.
Shetty sir, satellites are the result of incoherent interactions, while the quasi-particles are interacting coherently.
I mean, you mean the quasi-particle lifetime? Yeah, I guess so. there can be the satellites are indeed a result of incoherent interactions. For example, a particle, quasi-particle going through the system and scattering plasmons. That would give rise to a satellite. The lifetime of the quasi-particles can be coherent or incoherent processes. I mean, there can be electron scattering, there can be electron-phonon scattering. So
Terminology usually the main peak
yeah.
is called the coherent peak.
Okay, so that's where it's coming from. Okay, so then in that sense, the quasi-particle peak is the coherent peak. Yes. Yeah. But in general, it involves the lifetime involves all these things of electrons scattering from electrons and electrons scattering from the particles scattering electrons and other electrons in the system and scattering other phonons in the system, magnons in the system, anything that you can think of, whatever that is in a lifetime. So it no longer stays in that state; it loses energy to some other thing. So that is what that is actually the coherent process as it's called in the photon. Okay. So what I'm trying to say is that in principle, if you take this series that I was talking about and you insist on iterating this, because the point is you started with 0, you got this term, you plug this back into the original set of equations, go back, keep iterating this, you'll get more and more terms, right? You can show that the terms that you get are exactly the same as what you would have gotten if you actually just did Wick's theorem to actually find out the Green's function and so on. The difference is that the big theorem diagrams are of the same order, while here they come in different orders together. It really doesn't matter. The point is that it is exactly equal. Okay, so what do the diagrams really look like? Okay, so I guess I will stop after this. Okay, so what do the diagrams really look like? So if you look at the diagrams, actually, what if you write out the diagrams representing the self energy, here we call it the mass operator, but it's the same thing. Essentially, the first diagram looks like this, which is what I showed you, and this is the screen-Coulomb interaction, and this is the Green's function line. Second diagram looks like this, third one looks like this, and then you get more and more complicated things. Things which in principle are important, right? Depending on the physics that you're looking at. So there are some things, for example, in weakly correlated systems, usually it turns out this is good enough, right? What does that statement even mean? What that means is that if I sum this entire series, which I generally not, but if I did, right, then I would find that this contains the largest contribution. That's what it really means. Right? And you can show in some formal way that these are high order form diagrams that if it's weakly correlated, that the expansion parameter, because it's small, it basically goes to higher orders in that expansion parameter, and therefore it may be okay to let go of all of these terms when you are actually looking at weakly correlated. Okay. Similarly, there was actually Dyson-like equation for W as well. Okay, and here actually you can start with one bubble, which is what we had. We had two Green's function, if you remember. Two Green's functions, like the response is just electron hole pair generation. Right? That's what RPA response would be. So in principle, there is a whole series of diagrams that come with this as well. But in practice, what is being said is that we're going to just take the first diagram in this. Again, there are now further another first that I've introduced. Right? There's another first diagram in the W and first diagram in the G now. Right? That's what we're going to take, and that is good enough for describing the band gaps of weakly correlated systems. Now, if you show this to several people who are interested in very strongly correlated physics, they will say that some of these diagrams are actually very important in the kinds of things that they do, right? And it is true, but in weakly correlated systems, these are not so important, and so you can get away by neglecting. Okay, that's really this. Yeah. Should I stop now? I guess I should stop now, right?
There was a 5-minute break.
Okay, so I can go on for another 5 minutes. Again.
Yeah.
Okay, sounds good. So if you look at this GW diagram, and I motivated this in terms of let's say the Hartley-Fock equations, what you can do is you can actually recast the self energy in a slightly different way. Okay, and this is related to the fact that you can take the Green's function and you can write the advanced part of it and the retarded part of it, and you can break up the self energy based on that. And essentially, what you find is there's one part which is called the screen exchange, right? And the other part which is called the Coulomb hole. Okay, and this is what the breakup looks like. Another way to look at it, this is this is too complicated to understand. I mean, okay, maybe some of you can understand this, but this is, to me it's a bit too complicated to understand. So the way to do it is actually do it in the static limit, because then I start, the expressions become very simple, and it becomes more like the expressions for Hartley Fock. So if you go to the static limit of this Coulomb exchange, Coulomb hole and the string exchange, essentially you get expressions that look like this. Now, if you remember, right, if you remember from what we had done before, exchange was this replaced with B. Right, W replaced with B. That was what the bare exchange was. That was what the Hartley Fock exchange. So this looks exactly like that. And essentially what the screen exchange is nothing but the dynamic, not dynamically over here, but the screened version of this exchange. Basically, I've taken my W and replaced it to B, and that's all I've done. Right? But it turns out, in reality, when you do this formally, because you actually have if you do this correctly, you actually have another term, which is called the Coulomb hole, which is basically the interaction of this electron with all the excitations that you've generated in this. So this is basically nothing but the interaction of this electron with the screening charge that you've generated. And you have to keep both of these in your calculation to actually capture the physics problem. Okay. So in an actual implementation, which I will talk about in the next lecture, what you really end up doing is that you first end up solving the Kohn-Sham equation. That you know how to solve. Then what you do is you assume that the quasi-particle wave functions, see, you are supposed to solve this equation, right? Yeah. To solve this equation, what you do is you solve this equation. Okay, fine. But now what you have to do is you assume, you don't have to assume, but we can actually write this equation in that basis. But let's say for the sake of argument, for simplicity, you assume that this is what is usually done. You assume that these eigenfunctions are going to be the same. The quasi-particle eigenfunctions and the Kohn-Sham eigenstates are exactly. If you do that, then essentially, what you're left with in first order perturbation theory, what I have to do then is sigma minus bxc is my perturbation. I have this. I have solved it for bxc. If I define sigma minus bxc as my perturbation, then I can do first order perturbation theory, and in first order perturbation theory, this is what my correction to the DFT eigenvalue would be. Right? So again, I'm using another first order. Yeah. So in first order perturbation theory, this is what my quasi-particle energies become, and this is really what is done. So let me just quickly go through this because I've already described this. Essentially, what happens is you have a best G, best W approach, and we'll get to what this all means. What best G, best W means. I'll talk about that later. Essentially, what you do is you first solve let's start. You first solve the Kohn-Sham equations, right? You have DFT x and you have DFT eigenvalues. Then you use it to construct the polarizability. So because you have the eigenstates and eigenvalues, you have the Green's function. You have the Green's function, you can multiply the Green's function and get the irreducible polarizability, which is the RPA expression. Then from there, you can actually construct the W. You already have the DFT Green's function, so you can construct the self-energy, right? And then you can do a first order correction in your self-energy as the quasi-particle eigenvalues are DFT plus sigma minus Bxc, the first order correction. That's really what is done. Now, this is easier said than done. I was able to describe this in a single slide. The next lecture, I will try to describe the complications that come about when you actually try to do that. And then in the tutorial, we will actually try to run some calculations. I don't think we will all be able to run calculations. Perhaps we can just run the calculations you can see, and then you will have the code and the examples and everything, and you can run it on your own time. Right. So that is what we will try to show you for the GW part, and then I will in the next lecture I'll tell you what it means. So.
Thank you, Professor Jain, for a very clear talk. And now let's go to some questions and comments from the audience. Any questions?
So Manish, what I understand, so GW is essentially screen RT-POP,
That's it.
where the screening is being done by RTA.
That's
So
it.
this is what I'm saying.
That's
But if you look back, so I mean, I was just wondering whether this was first realized by Jain or it was already known before.
The RPS thing?
Not RPS screening, that RT-POP can be repaired by using a screen full of interaction.
I think what he did, and that's why he says that in his paper. I think he showed that replacing V by W is formally exact.
Okay.
So in that paper that I showed you, where I said that he says something about there's nothing new in principle. What he said, I think people realize how to talk, for metals give you terrible answers.
Absolutely.
So what he did is what he showed that if you do this in this way, right, of the equation that he said, it is formally equivalent to doing the full mixed theorem and the interaction in pair.
So it is formally correct. So that's
Formally correct. Okay. And then he also showed, which is also very important, that the first term is actually good enough in this formal expansion, at least for weakly coordinates. That I think that was at least that's my understanding of what it was.
okay.
Hello, sir.
Yeah.
So thank you for the nice lecture. So my question is, if you iterate W, right?
Yes.
Is it still RPA or it?
No, it will become beyond RP, right? I mean,
Beyond
it will be, of course, yeah. Because you have to solve the Dyson-like equation. So actually, no, let me sorry. So the self-energy for W is the irreducible polarization. Okay, so let me just go back for a second. So what is done is this is solved self-consistently. Exactly. So that you can do by doing an inversion. Basically, you can write it as an inverse, and you can write a matrix, right? And if you invert it, that is the same as solving this exact, right? But what goes in over here, the P naught, that is actually the RPA P naught. So the reducible polarizability that you get, see, you can get epsilon inverse, right? So the approximation is still within RPA because what you did for the polarizability is within RPA. Okay. If you want to add more stuff to this, you have to add the vertex over here and then solve the equation itself. Does that
So
answer?
that is effectively going beyond RPA.
It will go beyond RP. Yes, that is how you go beyond RP. Not that is how you go beyond RP. Yeah.
One more question from the audience. So you can unmute and say.
Professor Jain, thanks for the nice lecture. This is SETI. It's a followed up question that what I wrote. So usually satellites in photo emission come from when we perform experiment, there are several origins like surface states also will come as satellites. I think you refer to not from the surface states, but we also have another terminology like a coherent quasi-particle, incoherent quasi-particle. I think your satellite is something related to incoherent quasi-particle. That's what my question was.
Yeah, no, so what I was trying to say is that look, there can be satellites. So for example, you can have, as you said, they can be scattering to various kinds of states, right? So
Yes.
there are also these states where when the if you kick an electron out of the system, it has to get out of your system, right? So in the process of getting out, it can actually scatter plasmons, right? And it can lose energy to these plasmons. And I don't know whether you call that coherent or incoherent or what you call it, but that is the process that I was referring to with
The satellites.
some higher order process. Yeah.
Okay. Thanks. Yeah.
So I was just wondering, see, initially we start with RT-POP.
Yes.
And suppose I don't go by this, I just take a very simple interacting model like the Harvard model.
Yeah.
So ideally, I should have taken the single particle unit function of just solving the right part.
Yeah.
And then on top of that, I use the U,
Yes.
the correction part of
Yes.
U
Yes.
as a like this equation.
Yeah.
But suppose if you in DFT later on you are using DFT.
Yeah.
DFT when you are considering DFT solution,
Yeah.
that means you have already put the interaction there.
That is correct. But you remember that is correct. What you're saying is absolutely right. But there's no double counting here because when I do this, I subtract the part. Now there is some part which is built into the orbital, and it's the wrong part which is built into the orbital. Right? That part I am not subtracting out. But in principle, I am actually I can think of this as a basis. one electron basis. I can come up with any one electron basis and expand the self energy in that. Right? It is convenient for me to use the DFT one electron basis because all the rest of it is taken care of.
Yeah, so rather I would start with just the tight binding and then.
You can also use the tight binding. In fact, what they have done is they've shown that if you take U by W, U by W is small, or bandwidth, and then it works pretty well for when U by W is small. Let's say less than 1, 2. Okay. Beyond that, of course, all these other diagrams that you left out, they're going to come back and all the mod physics and all this other stuff, and
That's right.
people will look at this diagram and say this is the most important diagram. You will not get any mod physics.
I mean, I would say that I don't know how to make.
For a real material, you have no other option but to use Poncha model.
Correct.
Right. Getting a good tight binding model for a real material, right?
Yeah.
Right. Silicon possibly you can have.
Yeah, silicon possibly you can have, but yeah.
But then you also need the excited bands and so on because you have to put another.
Correct.
I mean, more concerned about the exactness of the method.
Yeah.
Because when you are adding this, these are corresponding to one of the configurations in many body basis.
I mean, what is
On
corresponding?
the many body basis, when you
Yeah.
take these diagrams. with
Yeah,
balls
yeah,
and other
yeah,
things,
yeah.
This is corresponding to one of the diagrams. Diagrams means like you have a many body basis. You start with some
Yes.
diagrams,
Yeah.
and then you need all the your exact wave function of the many body is.
So, but these are green functions, right? So
That's correct.
So you start-
if you connect it in the many body basis there,
Right.
it will be linear combination of some of the
of
bases.
basis states. Yes.
So basically, if you are using only finite set of these bubbles or diagrams,
Yes.
it will be only adding up to only finite number.
Yeah, absolutely. Yeah, absolutely. So there are so formally this is exact. Formally you can show that this is exact. But we do first of this one and we take the first of this one and there is a slew of diagrams here and a slew of diagrams here. But for weekly practice, it works. That's the idea. That's it.
Any other questions from the audience or online participants?
Prabhakar, you can unmute and say.
Hello, am I audible?
Hello?
Hello, am I audible? Yeah,
Yes,
so my question is regarding to the quasi-particle structure. So there was a quasi-particle wicks and a satellite. So my question, if the quasi-particle peak is more sharper, that means the lifetime of quasi-particle will be large, right?
Lifetime will be large. Yes, the weight of the peak is related to the lifetime.
Yeah.
Yes.
So my question is, what parameter which parameter will control this lifetime? I mean, if we consider the formula of the spectral function,
Yes.
so which parameter will control the lifetime of the quasi-particle, and what will be the when the satellite and the quasi-particle peak will be separated from each other? It might be will be some parameter so that the quasi-particle peak and satellites are submerged to each other, something
Yes,
like that.
it can happen, and depending on what you're studying, this changes from system to system. The lifetime
Okay.
also changes within the same system. If you're looking at, let's say, the highest occupied state versus if you right inside the band. So so all of these things that you're talking about are indeed real issues because you can have
Okay.
all of this getting mixed up with each other, and when you actually do a measurement, you can't actually disentangle these things out. So
Okay.
as to what controls it, I mean the lifetime actually comes from the electron phonon and the interaction of the system with other degrees of freedom, because otherwise you would have had an ideal state, right?
Yes.
So which would be a delta function. But because it talks to everything else, you actually get a broadening in this entire thing. So that depends on the system. So I can't give you a general answer for that. But what you're saying is true, that in principle it can actually merge with all these things can merge together and cause all sorts of difficulty in it.
Okay, thanks.
Okay, so since we are running out of time, so let's stop here and let's talk Professor Jain again. So here for 15 minutes behind the schedule, but shall we keep the time for?
We'll have a short break and then come back. I think we'll try to 11:15 we come back.
Okay, so let's do at 11:15.
Very good.
I mean, basically, you're